Hi everyone, welcome to Mr. Dave's Science Hub tutorials. In today's tutorials, we shall be looking at the concept of hybridization. Atomic orbitals can be combined and reshaped, much like dough, to make other orbitals of different shapes and properties. There are two basic types of orbitals that can result from such processes. We have hybrid orbitals, molecular orbitals. Molecular orbitals, they result from combinations of orbitals between atoms as bonding takes place to form molecules. Hybrid orbitals, they result from combination of orbitals within a given atom, either prior to or as bonding with another atom takes place. Therefore, hybridization is the mixing of atomic orbitals of similar energy in the same atom to form new equivalent hybrid orbitals. If we look at the valence share configuration of carbon, we find two paired electrons in the 2s orbital and two unpaired electrons in the 2px and 2py orbitals, one in each. In order to fulfill the octet's rule, carbon must use its four valence electrons when bonding to other atoms. However, only unpaired electrons can bond. That means that the two unpaired electrons occupying the 2s orbital must become unpaired before they can bond. Since the energy gap between the 2s and 2p orbitals is very small, one of the 2s electrons can be promoted to the empty 2p orbital, leading to the following situation. Now, the four electrons appear to be ready for bonding, but there is a problem. The 2p orbitals are known to be at right angles to each other. If bonding occurs in this state, the three equivalent p electrons would form three equivalent bonds oriented at 90 degrees to each other, and the s electron would form a bond of a different type and orientation from the other three. No such compounds exist. The simplest hydrocarbon, methane, is known to have tetrahedral geometry where the four C8 bonds are all equivalent and positioned at 109.5 degrees angles to each other. In addition, there are some carbon compounds where the bonds angles are 120 degree or even 180 degree. The shapes and relative position of the valence orbitals in atomic carbon do not explain the shapes and relative positions of the bonds in carbon compounds. Going back to the carbon model with four unpaired electrons in the valence shell, we can take it as a point of departure for formation of hybrid orbitals. The first step is to take either two, three, or all four of those orbitals and equalize their energies. Let's say that we take all four of them and form four equivalent new orbitals. These orbitals are now of the same energy, which is intermediate between those of the original 2s and 2p orbitals. At the same time, we cannot name the new orbitals s or p, for they are neither. We have to find a new name that reflects the fact that they were created from one s orbital and three p orbitals. We will call them sp3 orbitals. The process that leads to their formation is called sp3 hybridization. All four sp3 orbitals that result from this process are equivalent. That means that they have the same size, shape, and energy. According to the VSEPR, valence share electron pair repulsion theory, such orbitals will orient themselves in 3D space to be as far apart from each other as possible. The resulting shape is then a tetrahedron, where the carbon nucleus is at the center and the orbitals point to the corners of the tetrahedron. The RD angle between orbitals is then 109.5 degrees. When sp3 hybridized carbon bonds to hydrogen, it forms methane, whose geometry is known to be tetrahedral. A 3-3 representation of methane. The single lines represent bonds that are positioned on the plane of the paper. The solid wedge represents a bond coming out of the plane of the paper towards the front. The broken wedge represents a bond going behind the plane of the paper towards the back. Types of hybridization. sp3 hybridization is when one electron from S combines with another one electron from p orbital to form sp hybridized orbital, and the process is known as sp hybridization. sp2 hybridization, one electron from s orbital and two electrons from p orbitals when they combine together to form a hybrid orbital. This process is known as sp2 hybridization. sp3 hybridization is when one electron of the s orbital combines with three electrons of the p orbitals to form sp3 hybridized orbital, and the process sp3 hybridization. The same thing as sp3 hybridization and sp3d hybridization. Looking at this diagram, you will understand the shapes, the orientation of all the types of hybridization in space, as well as their respective angles. How to determine hybridization? You first count the number of atoms connected to it. You count the number of lone pairs attached to it. Then you add these two numbers together. If you find out that your number is 4, then the atom is sp3. If 3, your atom is sp2 hybridized. If 2, your atom is sp, and if 1, your atom is probably hydrogen. The main exception is atoms with lone pairs that are adjacent to pi bonds. This is just the illustration on how to count the number of or to determine your hybridization. Purpose of hybridization. Hybridization explains molecular shapes. It also explains bond angles. It produces stronger and more stable covalent bonds. Condition of hybridization. Hybridization occurs before bond formation. It involves orbitals of nearly the same energy. Takes place within the same atom. Characteristics of hybrid orbitals. Hybrid orbitals, they must be equal in energy. They must be degenerate. They must have specific orientation in space. They all have shapes. They also form sigma bonds. Importance of hybridization. How is hybridization very important? It predicts the geometry of molecules, explains chemical bonding and molecular stability. It also helps in understanding the properties and the reactivity of compounds. Applications of hybridization. Hybridization can be applied in organic chemistry, also in biochemistry, pharmaceutical chemistry, and material science. If you like and enjoy watching this video, don't forget to click the subscription button and also turn on the notification bell. I will see you in the next video. Thanks for watching.